Somewhere in a lab in Vancouver, a machine that looks nothing like a computer just did something that, according to its creators, should have been physically impossible. It solved a problem in 20 minutes. The same problem, run on one of the most powerful supercomputers ever built, would take nearly 1 million years to finish. Not a few years, not a few decades. 1 million years, using more electricity than the entire planet consumes in 12 months combined. If that sounds like science fiction, that's because for most of computing history it basically was. But in March of 2025, a company called D-Wave says it turned that fiction into a peer-reviewed published fact. And the fallout from that claim is still shaking the entire quantum computing world today. Let's back up and actually understand what happened here, because the claim itself is almost too big to process in a single sentence. D-Wave is a quantum computing company based in Canada, and unlike the massive names you'd expect to hear in this conversation, like Google or IBM, D-Wave has spent decades building a very specific, very different kind of quantum machine called a quantum annealer. Instead of trying to build a general-purpose quantum computer that can run any algorithm you throw at it, D-Wave built something more specialized, a machine, designed specifically to explore complex, tangled optimization problems by letting quantum physics itself do the heavy lifting. D-Wave has actually been around far longer than most people realize, and that history matters for understanding why this particular announcement landed so hard. The company was among the very first pure-play quantum computing businesses to list on a major stock exchange, and for years it operated in a strange kind of professional limbo, respected by physicists who understood quantum annealing, but dismissed by plenty of skeptics who questioned whether its machines were doing anything meaningfully quantum at all. That skepticism wasn't baseless either. Quantum annealers are a fundamentally more limited technology than the general purpose. Gate-based quantum computers companies like Google and IBM are racing to build, and for a long time D-Wave struggled to prove its narrower approach could produce results classical computers genuinely couldn't match. This announcement, published through peer review in one of the most respected scientific journals on Earth, was meant to finally settle that argument once and for all. The specific problem D-Wave tackled involves something called a spin glass. If you've never heard that term before, don't worry, because the concept, stripped of its jargon, is actually fascinating. A spin glass is a type of magnetic material where the tiny magnetic components inside it, called spins, don't line up neatly in one simple pattern. Instead, they get pulled in competing directions by their neighbors, creating an almost impossibly tangled web of interactions that fight against each other constantly. Simulating exactly how that tangled system evolves over time, predicting precisely how all those competing magnetic forces play out, is one of the most computationally brutal problems in all of physics. Classical computers, the kind sitting in your home right now, struggle enormously with this kind of problem because of something called exponential scaling. Every time you add just one more magnetic particle to the simulation, the number of possible configurations doesn't grow by a little, it roughly doubles. Add a few dozen more particles, and suddenly you're dealing with more possible configurations than there are atoms in the observable universe. No supercomputer, no matter how many processors you throw at it, can simply brute force its way through math that explodes that violently. Quantum computers, at least in theory, sidestep this problem in a genuinely elegant way. Instead of checking every possible configuration one at a time like a classical computer would, a quantum system made of actual quantum particles can behave like the very physics it's trying to simulate. D-Wave's machine, called Advantage 2, used more than 5,000 qubits arranged specifically to mimic the behavior of a real spin glass. In effect, they weren't just calculating an approximation of the physics on a chip. They were letting the chip become a live physical stand-in for the exact system they wanted to understand, obeying the same underlying quantum rules the real material would follow. To understand why that distinction matters so much, it helps to think about the difference between calculating something and simply becoming it. A classical computer simulating a spin glass has to painstakingly calculate step by step how thousands of individual magnetic particles would interact with each other over time, checking possibility after possibility using ordinary arithmetic. A quantum annealer skips that calculation entirely, because its own qubits are themselves tiny quantum systems obeying the exact same physical rules as the material being studied. The machine doesn't need to calculate the answer at all. It simply evolves naturally into the answer, the same way the real physical material would, just inside a carefully controlled chip instead of out in the natural world. That's the entire conceptual leap behind quantum annealing, and it's part of why, when it actually works as intended, the speed up over classical brute force calculation can look almost absurdly large, and the results, according to the peer-reviewed paper published in the journal Science, were staggering. For the largest, most complex configurations tested, D-Wave's quantum annealer produced results using roughly 36 microseconds of actual runtime, plus additional overhead for running the process multiple times to confirm consistency. The comparison point was Frontier, a supercomputer at Oak Ridge National Laboratory that ranks among the most powerful classical machines ever constructed, built from massive clusters of graphics processing units. According to D-Wave's estimates, Frontier would need somewhere in the neighborhood of 1 million years to match that same level of accuracy on the hardest instances of the problem. Let that sink in for a moment, because the scale here is genuinely difficult for the human brain to process intuitively. 1 million years is longer than modern humans have existed as a species. It's longer than agriculture has existed. It's longer than most estimates for how long our entire species has walked the Earth. And D-Wave says its machine matched that time scale of computational effort in about the time it takes to make a cup of coffee. Naturally, when a claim this enormous gets published, the scientific community doesn't just nod along and move on. It digs in hard. And that's exactly what happened here, almost immediately. Within weeks of D-Wave's paper going public, researchers from other institutions started publishing rebuttal after rebuttal, each one chipping away at different pieces of the million-year comparison. A team from the École Polytechnique Fédérale de Lausanne in Switzerland claimed they could replicate results that D-Wave estimated would take more than 150 years on Frontier, and they did it in just a few days, using nothing more exotic than 4 ordinary graphics processing units. Other researchers went even further. A separate group rushed to publish their own competing paper, arguing they had solved the exact same underlying problem using an ordinary classical computer powered by just 4 GPUs, completing the task in roughly 3 days. If accurate, that single result alone would dramatically undercut D-Wave as headline comparison, suggesting the true classical runtime wasn't anywhere close to 1 million years, but rather something dramatically smaller, achievable with modest, off-the-shelf hardware, rather than an entire supercomputer facility. This isn't actually a new pattern in quantum computing. It's worth understanding why, because it says something important about how these breakthroughs tend to unfold. Time and time again, a quantum computing company announces a dramatic result, framing it in terms of some almost unbelievable classical runtime, only for classical researchers to respond within weeks or months by developing smarter, more efficient classical algorithms that dramatically close the gap. One frustrated commentator, reacting to yet another version of this exact story playing out publicly, described it as something close to a running joke in the field. The company claims an achievement that would supposedly take 1 billion years classically, and shortly afterward, someone proves them wrong, using a fraction of the claimed effort. Google faced almost exactly the same pattern back when it first announced its own quantum supremacy claim years earlier, using a completely different type of quantum chip built on the gate model approach rather than annealing. At the time, Google claimed a task that would take a classical supercomputer roughly 10,000 years had been completed by its quantum processor in about 200 seconds. Within months, researchers at IBM published a rebuttal, arguing that, with sufficiently clever classical optimization, the same task could actually be completed in a matter of days rather than millennia, not eliminating the quantum advantage entirely, but shrinking it dramatically from the original headline figure. That exact dynamic, a jaw-dropping initial claim followed by a much more modest, contested revision, has repeated itself often enough now that seasoned observers in the field have started treating the very first announcement of any new quantum milestone as, at best, a promising opening bid rather than a final, settled verdict. So does that mean D-Wave's entire announcement was empty hype? Not exactly, and this is where the story gets genuinely more interesting than a simple yes or no answer. D-Wave and its supporting scientists have pushed back firmly against the rebuttals, arguing that the classical methods used in the counterclaims don't actually match the same level of accuracy the quantum annealer achieved on the hardest, most complex instances of the problem. In other words, according to D-Wave, critics may have found faster classical shortcuts, but those shortcuts came at the cost of precision, essentially trading accuracy for speed in a way that doesn't fairly represent an apples-to-apples comparison. This back and forth has played out largely through competing papers and public statements rather than any single definitive resolution, and that's genuinely frustrating if you're hoping for a clean, simple answer to walk away with. D-Wave insists the disputed classical results, while genuinely fast, sacrifice enough precision on the largest, most complex test cases that they don't actually solve the same problem the quantum annealer solved. Critics counter that the precision difference, even if real, might not matter much for most practical applications, and that D-Wave's million-year framing was always designed to maximize headline impact rather than scientific precision. Both sides have a point buried somewhere in their argument, which is exactly why, more than a year after the original paper's publication, the dispute still hasn't fully settled in either direction. Independent voices in the field have offered a more nuanced middle ground here too. Researchers not directly involved in either side of the dispute have pointed out that Classical approximate methods based on tensor networks and neural networks genuinely do struggle to match the same accuracy the quantum annular delivered within any reasonable time frame, even if they can produce a rough, less precise version of similar results relatively quickly. The paper itself, in fact, makes exactly this argument directly, stating that leading approximate classical methods simply cannot achieve the same level of accuracy the quantum machine reached, at least not without paying an enormous computational cost of their own. Seth Lloyd, a professor of quantum mechanical engineering at MIT, offered a perspective that captures the genuinely balanced reality sitting underneath all this noise and back and forth. He noted that large-scale, fully error-corrected quantum computers, the kind capable of running literally any algorithm reliably, remain years away from practical reality. But quantum annulars, like D-Wave's machine, despite being far more limited and specialized in what they can actually do, are already capable of probing genuine features of real quantum systems today, right now, not in some distant hypothetical future. That distinction matters enormously, and it's the part most headlines skip entirely in their rush toward a dramatic million-year comparison. D-Wave's advantage isn't a general-purpose quantum computer capable of breaking encryption, running arbitrary software, or replacing your laptop anytime soon. It's a highly specialized tool, purpose, built to simulate one very specific category of physics problem, the kind involving magnetic materials and complex competing quantum interactions. Within that narrow lane, the evidence increasingly suggests something genuinely remarkable is happening. Outside that narrow lane, the machine simply isn't built to compete at all, and D-Wave has never seriously claimed otherwise. It's also worth mentioning that this dispute hasn't just played out in academic journals. It played out in the stock market, too, in real time, with real money attached. D-Wave is a publicly traded company, and news of a peer-reviewed quantum supremacy claim sent noticeable waves through investor sentiment around quantum computing stocks generally, not just D-Wave's own shares. That's worth flagging because it adds an entirely different layer of incentive to this story beyond pure scientific curiosity. A publicly traded company has genuine financial motivation to frame its results in the most dramatic, headline-friendly way possible, and that doesn't automatically make the underlying science wrong, but it does mean healthy skepticism toward the framing is exactly the right instinct to bring to a story like this one. Why does any of this actually matter beyond academic bragging rights between competing labs? Because simulating magnetic materials accurately has real, tangible applications across multiple industries, not just abstract physics curiosity. Understanding exactly how new magnetic materials behave at the quantum level helps researchers design better sensors, more efficient electric motors, improved data storage technologies, and next-generation batteries, all without needing to physically synthesize and test thousands of expensive experimental material samples in a lab first. If quantum annulars really can model these interactions faster and more accurately than classical supercomputers, even within this one narrow category of problem that represents a genuine practical head start for entire fields of material science research. Think about how much time and money currently goes into physically manufacturing and testing new material samples in laboratories around the world, often through years of painstaking trial and error before a single useful discovery emerges. If quantum simulation can reliably predict which candidate materials are actually worth building in the first place, narrowing thousands of possibilities down to a handful of genuinely promising ones before anyone spends a single dollar on physical synthesis, that alone could meaningfully accelerate research timelines across electronics, energy storage, and advanced manufacturing, regardless of how the exact million-year comparison eventually settles. Multiple prominent physicists involved in reviewing or commenting on the work have echoed this same cautious optimism. Hidetoshi Nishimori, a physics professor at the Tokyo Institute of Technology, described the paper as marking a significant milestone in demonstrating the real-world applicability of large-scale quantum computing. Alberto Nogueira, a senior staff scientist at the University of British Columbia who worked directly on the research, argued that the results expose the genuine impracticality of current state-of-the-art classical simulation methods for this specific category of quantum magnetic dynamics, opening a door for quantum technologies to answer scientific questions that might otherwise remain permanently out of reach. So where does the actual truth sit? Somewhere between D-Wave's triumphant press release and its critics' pointed rebuttals? Probably closer to the middle than either side's most dramatic framing would suggest. D-Wave almost certainly did demonstrate something genuinely difficult for classical computers to replicate at the same level of precision, at least using currently known algorithms. But the specific million-year figure, dramatic and headline-friendly as it is, likely oversells the gap somewhat, since classical researchers keep finding cleverer, faster approximate methods every time a new quantum claim like this gets published. That doesn't make D-Wave's underlying result meaningless. It just means the real story is messier, more contested, and honestly, more scientifically interesting than a single tidy headline number could ever fully capture. This pattern, by the way, is actually a healthy sign for the field, even though it might look like chaos or contradiction from the outside looking in. Science is supposed to work exactly this way. Someone makes a bold claim, backed by real data and peer review. Other researchers scrutinize it fiercely, poke holes wherever they can find them, and publish counter-evidence when they succeed. Through that adversarial process, repeated over and over across dozens of competing claims, the field as a whole inches closer to understanding where quantum computers genuinely outperform classical machines and where the gap is smaller or more contestable than initial announcements suggest. Nobody gets to simply declare victory unchallenged, and that's exactly how genuine scientific progress is supposed to unfold. For everyday people watching this unfold from the sidelines, the practical takeaway isn't that quantum computers are about to replace your laptop, your phone, or anything else you use daily anytime soon. They're not, and nobody serious in the field claims otherwise. The practical takeaway is that we're living through the earliest, messiest chapter of a genuinely new computing paradigm slowly proving itself capable of solving specific, narrow categories of problems that classical machines struggle, with one contested claim and one fierce rebuttal at a time. It's less like watching a finished revolution and more like watching the opening chapters of one get written in real time, disputes and all. It's worth zooming out for a second and asking what genuine, undisputed progress actually looks like in a field this young and this contested. It rarely arrives as a single, dramatic headline that everyone immediately agrees on. It arrives slowly through a gradual narrowing of disagreement, as rebuttal after rebuttal chips away at the most exaggerated framing until something smaller, more modest, but far more durable remains standing. If, a year or two from now, both D-Wave's supporters and its harshest critics broadly agree that quantum annealers hold a genuine, if more modest, advantage over classical computers for this narrow category of magnetic material simulation, that quieter, less dramatic consensus will actually represent far more real progress than the original million-year headline ever did on its own. If you find this kind of story fascinating, the messy, contested reality behind the flashy headlines that get shared without any of the crucial nuance attached, make sure you like this video and subscribe for more. This channel exists specifically to dig past the dramatic press release version of these stories and into what's actually verifiably happening underneath all the noise, one contested claim at a time. Because here's the thing worth remembering the next time you see a headline claiming some new machine just did the impossible in 20 minutes. The most exciting scientific claims are almost never simple, clean victories decided in a single afternoon. They're the opening move in a much longer argument, one that plays out over months and years of competing papers, aggressive rebuttals, and careful, patient scrutiny from researchers determined to get the real answer right. D-Wave's quantum annealer may genuinely represent a meaningful step toward useful quantum advantage, or it may simply be the latest chapter in a familiar cycle where classical computing keeps finding clever new tricks to close a gap that once looked insurmountable. Either way, the actual million-year answer isn't going to arrive in a single press release. It's going to arrive slowly, contested paper by contested paper, exactly the way real scientific progress always does. And that, honestly, is a far more interesting story than the one the original headline promised you. A world where every big scientific claim landed as a clean, uncontested fact would actually be a little suspicious, because real breakthroughs almost always survive scrutiny by getting sharper, not by avoiding it entirely. So next time you see a dramatic quantum computing headline promising some impossible feat measured in millions of years, remember this story. Wait for the rebuttals. Wait for the second and third papers. That's not cynicism, and it's not dismissing genuine progress when it happens. It's simply understanding how science actually works. One contested claim, one careful correction, and one narrowing disagreement at a time, until eventually something true and durable is left standing at the end of it all.